Okay, so let's have a new question, and this will be the first example we have in the tutorial today, which is going to be about the Acme thread power screw is loaded with in tension with a force of 133.44 Newton, or what equals to 30,000 pounds. What size of the screw from table 71 should be used to maintain the tensile stress below the 68.95 megapascal or 10,000 psi? And what will be the required axial length of the nut on the screw that transfer the load to the frame of the machine if the shear stress in the thread must be less than 41.37 megapascal or 6,000 psi. Now you can see that both the stress should be below and the thread should be below. That means when we're going to do the selection for the area, it should be above what we are going to calculate, not below. Okay, because you know that the higher the area is, the less that the stresses are. So let's go do the calculation. First, you need to write down the parameters: 133.44, 68.95, or 41.37, or you write down the pounds, pounds per square inch, and so on. So let's start with the solution steps. First, it is a simple problem on normal stress for the shaft. And the required tensile stress area can be calculated, as you remember, from the load divided by the stress. So the load divided by the stress will give me the tensile stress area. So you remember that we have the table here. We're going to use this one to compare the tensile stress area with the tensile stress area from the table 71. Sorry, I just took the range from 2 to 3 inches, and we will find out why I selected that very soon. So again, to put the parameters in, okay, we look at the 133.44 divided by 68.95 megapascal, and this will give me the area to be 1,935 millimeters square, or what is equal to 3 inches square. Now, I'll try to do it using the inches and the psi units. Just give me once again. I'm going to bring the calculator in front of you. So where's my calculator? Okay, I have now the calculator. I'm going to do the calculation to find the exact area in inches square. So I will get back to here, to this question, and get the parameter from. So we need to know first what is the load. The load was 30,000 pounds, so I get to have 30,000 pound divided by the 10,000 pounds. And this will give me 3 inches square. So now I know the area is 3 inches square. That's in case if you would like to do it using the IP units. It shouldn't be something hard to be done. So now I got the area to be 3,000 inches. And now I'm going to find that from the table. I have here 2.982 and I have 3.82. I selected the second one because we said that we need to this stress not to be more than or less than the 10,000. So I would like to choose higher area in order to provide me with a less value for the stress. So from the table here, 71, we choose the 2.5 inches diameter, will give me the end value or number of thread per each inch to be equal to 3. And the tensile stress area is going to be 3.802, and the shear stress area to be 4.075 inches square. Now we continue with the solution. I would like to know what will be the length of the knot. So we are going to calculate how much area I need for the stress. So you remember that we said that the load was 133 and the value for the tau was maximum 41.37 megapascal. So I find that the area is going to be equal to 3,225 millimeters square, or is going to be equal about 5 inches. Now, again, you remember that the area we got from the table was 4.08. Okay, so the area we got is 4.08 or 4.07, and thus I need 5 inches. So each 1 inch will give me 4.075. So how many inches I need to get the 5 inches square is going to be the question now. So if I'm going to bring back my calculator, it's simply going to be is that 5 inches is required, 4 inches per 1 inch, and then I will do the following, just simply 5 divided by the 4.075. So I need 1.226. That's in inches. If I'm going to multiply that by 25.4, I need it not to be 31.2 millimeter in length. Okay, so yep, that's what we're going to do. And we're going to find that the axial length is going to be equal to 31.2 millimeter. So that's it. That's a question. As simple as that. The other one is going to be not much different from it. And the required length now is 31.2 millimeters. We're going to come to another example very soon. And well, actually, it's going to be continue for this question. So it's going to be nice to put them in one video. So now we just need to compute the torque required to raise or lower the load of the 133.44 Newton with the Acme screw selected in the example 51. Use your constant friction to be 0.15. So if I'm going to give you the time and the total raise, you will also find the power, but it's not required in this question. However, now it is given to us the constant friction, and I only need to get some of the parameters to complete the answer. So the first one is, these are the parameters we can get. We can get the value of the number of threads per 1 inch, the pitch value, the minimum pitch value, diameter, the tensile stress, and the shear stress. So we're going to get the following parameters. First, the phi is 14.5, that's pressure angle. The constant friction is 0.15 is given in the question. The dP is now 2.2939, that's what we get from the table. And the F value is 133.44. The L, or how much we're going to move for one rotation, is going to be 1 over 3, which is going to be 4.85, 8.458 millimeters. And then I can calculate the lambda, because the tangent of the lambda is going to be equal to the L divided by the pi dP. Now, the L is 8.45. Okay, let's get the calculator. Okay, so once again, we need the L divided by the pi dP. So well, now the dP is given to us as 58.265 times pi. Okay, 2, and reverse that multiplied by the 8.45. Okay. Equal to that. This is the number, and I can find the value for the lambda. It's 2.64. Okay, so we got the value for the lambda, and this will help me to continue with the answering. So, yep, that tangent of the lambda can be calculated now, and that's mean the lambda is going to be 2.65 degree. Now, we're going to use the equations to calculate the torques. So the two equations we have for the raising and for the lowering the load are already being given, then I can apply the parameters within. So the X is 133 kilonewton, 58.265 is the dP divided by 2. That's the part 1. Now you can put that, of course, on an Excel sheet calculator, right? Now we have here the cosine of the phi, cosine tangent of the lambda, plus the coefficient of friction, cosine of the phi minus the coefficient of friction multiplied by the tangent of the lambda. and put all the parameters in, and we can find the answer. And the same thing is going to be done for the other side. Just remember that the only thing we had is we just changed by putting a minus here and a minus here, and everything else is going to be the same. So by putting the parameters in, we'll find that the torque required to raise up the load is going to be 787.9 Newton meter, while to lower it, we're going to need 1419.3 Newton meter. I'm going to give you in the class the time you should be and the distance to be moved. You can continue as we done in the examples earlier to find what will be the power uh, required for the raising or lowering the load. And also the same thing, we can calculate the efficiencies. We can add that anytime. So we'll mention that.